So once you design the timing of the signal, now you have to check if the timing is enough for pedestrians or not. For that you must know how much time the pedestrian requires. Okay, for how much time or how much time you should give to the pedestrians to have a safe crossing. So the time required by the pedestrian is GP. Okay, so GP is time required by the pedestrians. Okay, I indicates the phase or the direction, because in each direction pedestrian may require different time. Okay, so GP is the time required by the pedestrian. I indicates in which direction. Okay, so you can see it is comprised of two parts. PW means pedestrian walking time. PW is pedestrian walking time, and then we have PC, which is pedestrian clearance time. Okay, pedestrian walking time and pedestrian clearance time. Where is walking time? There is a table for this. Okay, so this table gives you the values of green signal for the pedestrian. Once the signal becomes green, how much time it should remain green for the pedestrians. Okay, and it is according to where you are doing it, the case, the intersection, the location, and so on. Okay, so in couple of cases they have given us a range. You want to be safe, you can take the maximum from the range, no problem. Okay, even if you take the minimum, it is allowed. Okay, clear? Pedestrian clearance time. Pedestrian clearance time is a time when the signal is flashing. The yellow signal starts flashing for the pedestrian. Okay, so if you are the pedestrian, you see signal flashing, what would you do? Run for your life, right? Literally run for your life. Okay, so we calculated using this equation, which is L upon SP. What is L? Length of the crosswalk. L is length of the crosswalk, how far he has to cross, and SP is the speed of pedestrians. SP is the speed of pedestrians. Okay, there is a speed given in the table. Can you see it? How much speed is given in the table?
Distance by time.
3. Okay, 3 feet per second. You can go maximum 3.5, not more than this. Okay, so you can use a speed, you can find out your own speed, you can go and observe the speed of the pedestrians. Okay, or you can use 3 or 3.5, these values are allowed. Okay, and then length of the crosswalk, obviously it depends upon the road. Okay, so you can calculate the clearance time from here. So once you know the time of the pedestrian, required time of the pedestrian, now you will check it with the signal. You will check it with the signal. So pedestrian will cross when the signal is green for parallel traffic. Okay, so I want to cross towards east. So I am standing here and I am looking at when the vehicles will start going towards east, and I will cross with them, right? So if, for example, I need 10 seconds to cross, okay, and the signal for the vehicles is exactly 10 seconds, no problem. It's green for 10 seconds. 10 seconds is enough for me to cross. I will cross, no problem. Okay, but let's say I have a problem with my leg. I have a kid with me or something. Okay, so I'm taking more time. Let's say, what will happen after green? Yellow, right? Yellow. So if I'm taking more time, the signal has become yellow for these vehicles, the parallel vehicles. Is it safe for me to cross? Still it is safe, right? Because the other traffic is still stopped. Other traffic is still stopped. Okay? But let's say I have more problems with me. Okay? My wife starts calling as well. So I cannot miss it, right? Get killed at home or at road. What is better, right? So I take more time now. A couple of seconds more. What will happen after yellow? Yellow is consumed now. All red. All red. Okay? If I am still on the road during all red, is it safe for me or not? Huh? because the other traffic is still stopped. Remember, I'm not concerned about the traffic which is going with me. I'm concerned about traffic which is the other side. The other side is still red. Okay, so if I reach the other side at the end of all red, still it is good enough. Clear? Clear? Okay, so if the pedestrian time is exactly equal to green, no problem. If it is exactly equal to green and yellow, no problem, safe, right? If it is exactly equal to green, yellow and all red, still safe. But if you go to the last case, there is no margin now. There is no risk factor now, factor of safety. Okay, so after that, the signal will become green for the other side. Okay, so now it is unsafe. So you don't have even a single second more. Okay, so if I made the signal so that the green is equal to my time, even if I take more time, no problem. I still have 3-4 seconds more. If it is equal to up to yellow time, no problem. I still have a couple of seconds more. Okay. If it is equal to all red, no problem, but there is no contingency now. Okay. There is no factor of safety. Clear? Clear. So all these three cases are allowed, but you should know that you are reducing your margin. Okay. You are at the edge now. Okay. Let us look at how we do the adjustment of signal timing. Remember, we already designed the signal, we calculate the green time. Okay, so this signal has two phases. For each phase I have green, yellow and all red. Lost time is also given, and then I have the minimum required pedestrian time for this phase. Okay, so phase A, wherever the phase A is going, pedestrians are going with them. Okay, clear? Now they are saying that we will take the worst case. The worst case is pedestrian required time is equal to green plus capital Y. Capital Y is what? Yellow and orange. Okay. So even if you go up to that point, we will still pass the signal. We will still let the design go. Okay. So now first of all we need to check. We need to check if we are meeting the pedestrian criteria for both these phases or not. Okay. So if you do it for the first phase, phase A, then how much is green, yellow and all red? How much is it? 40 plus 3 plus 2. How much? 45 seconds. Is it more or less than the pedestrian? More. So no problem with phase A. Okay. Phase B, 15 plus 3 plus 2, 20 seconds. So what is it now? Less. So now we have a problem, right? Now I have to change. Change what? Green time. Okay. Yellow and all red you cannot change. We have separate equations for them. Okay. And somebody said change pedestrian time. So it requires a gun, which we don't have. Huh? Put a gun to their head. Run. Okay. Which we don't have. So the only thing which you can change is green time. Okay. Now how do I change this? I want it to be how much?
At least
20?
Yes,
20. 30. Okay. So I want the phase B total time to be at least 30, right? So 30 equals to GB plus 3 plus 2. The yellow and all red. I will not change. So this means what? GB equals to what? Yeah. Clear? Okay. Now, the next thing is, so I know GB and GA doesn't have a problem yet, but I need to change it. I'll still change it. Okay. Why? First of all, if I don't change it, it will be very easy for you, which I don't want. Okay. Secondly, the signal, when the signal becomes green for B, it is what for A? No. When the signal is green for B, that means it is red for A. In that much time, there was some traffic which was coming onto A side. Okay? And when the signal became green, that time was enough for this traffic to move. Okay? So let's say in 15 seconds of green, when the B was green for 15 seconds, I had a queue of 7 vehicles on the A side. Okay, so 40 seconds are enough for 7 vehicles. But when you increase the time of B, now you will not have 7 vehicles in the queue on the A side, because A is becoming red for a long time, right? Okay, you are giving 10 seconds extra here, right? That means 10 seconds extra red on the other side. Okay, so now the queue will be longer. Okay, so that means A also needs more time to get rid of the extra vehicles in the queue. If you don't do this, the queue will keep on getting longer every time. Okay, eventually the signal will fail. Okay, so I need to adjust the total time as well. I need to adjust the total time. For this, first of all, so I'm now playing with my design. So for playing with the design, I must calculate the effective times, effective green times. Okay, so these are the existing effective green times for A and B. How do I calculate them? Using this equation. Okay, so I had the green time. For example, if you look at A, the green time is 40. Capital Y, which is yellow and all red, 3 plus 2. Minus lost time, which is 5. So 40 plus 3 plus 2 minus 5, which is 40. Okay, clear? And same thing for B. So I already know the existing time for A and B, the effective green time for A and B. Okay, then the next thing I will do is calculate the current cycle length. Cycle length is made up of phases, right? How many phases I have? 2 phases. Okay, and a phase includes green, yellow and orange. A phase includes green, yellow and orange. If I want to calculate total cycle length, I will add green, yellow and orange for A, and I will add green, yellow and orange for B, which is what we have done. 40 plus 3 plus 2 for A, 15 plus 3 plus 2 for B. Clear? No, at the end of A, it again happens. Get my point? This is, so for example, if you take 2 seconds, which is happening at the end of A. Okay, so this is all red at the end of A. Then again, an all red will happen at the end of B. Okay, so I have to add both of them. Clear? So that's why we don't consider red, because red can be confusing. We have an all red and we have a red for 1 phase and 2 phase, and that's why we don't consider it. Okay, when you add all the phases, green, yellow and all red, the red time is already included, right? The total red time of A was what? 15 plus 3 plus 2. This is the total red time of A, right? When the signal was green for B, it is red for A. When it is yellow for B, it is still red for A. When it is all red, obviously it is red for A. Okay, so red for A is already included. Okay, so just to avoid confusion, okay, we just add the timings which you already know and you calculate. Red you already know is being added now. Clear? Clear? Any questions? Okay. Now moving on. First of all, I have the old cycle length. I'll calculate the new cycle. Okay, and I have to maintain the ratio. Okay, I know the old time of phase B, which is 15. I know the new time of phase B, which is 25. Okay, according to pedestrian time. Okay. If you convert it to effective green, it will remain the same, right? Plus 3, plus 2, minus 5, like we did here. Okay. So effective green or the actual green doesn't matter. Okay. I know the old cycle length, which is 65. I want the new cycle length, which is C dash. Okay, clear? So, tell me the new cycle length. One 108.3. Okay, and we said we don't normally round it up to the nearest 5 or 10 seconds, so we can make it 110 seconds. Okay, now I need the time for A. I need the time for A. Okay, I can go back to this equation because I have only two phases. I have only two phases. I can go here. I know the time of B. I know the new cycle length, new time of B. The only thing remaining is okay, the green for A. I can do this. Okay, this in this case it is very easy. And you can do it, no problem. So if you do this, okay, so new cycle length 110, which is equal to GA plus 3 plus 2 plus the new GB plus 3 plus 2. So GA equals to what? 75. Okay. This is very easy because only two phases. And you already know one of the phases. But what if we have 3, 4, 5 phases? What we'll do? Okay. In that case, we will use the ratio. Okay. So what we will do? We have the. We will take the ratio for the effective green time, which are the same in this case. But the ratio is for the effective green times. Okay. So first of all, I will calculate the total effective green time. Total effective green time equals to what? Cycle length minus what? Cycle length is 100 milliseconds, right? Minus what? Lost time. Cycle length minus lost time of all phases. Lost time of all phases. So I have 5 seconds for phase A, 5 seconds for phase B. So this is 100 seconds, right? Clear? Okay? Clear? Now I will divide or distribute the cycle length in both phases according to the ratio of the time which I already had. Okay, how? So I want the new time for A. Okay, so what I will do, I will take total time I have, green, multiply by the old time of A, which is 40. Divide by, what is 60? What is 60? 65, yes. Why 65? No. The previous cycle was 65. Previous cycle was 65. I want the total effective green time.
65 minus
Yeah. Or you can just do this process. Got it? It could be difference because Obviously, you are taking ratio and you are doing simple addition, subtraction there.
72.7.
But this one is effective green, so you still have to convert it to. Okay, but anyways. Now, this approach, the ratio approach, will work for 3 phases, 4 phases, 5 phases, doesn't matter. Okay, even if we have 10 phases, okay, so you will put the old time of the phase on the top and the total effective green at the bottom, that's it. Okay, numerator is the old time of that phase which you are calculating, and the denominator is the total effective green time. Clear? Okay, so if it is 10 phases, I will add 10 terms in the denominator. Okay, and I will use the numerator one by one for each phase. Got it? Clear? Any questions? Okay, so the second approach can work with any number of phases, and you can see there's a little bit of difference in the answers as well, because obviously ratio and addition, simple addition, they're supposed to be. But in the end, if you are when you will add, the timings will add eventually. Okay, clear? Okay, thank you. We have a new topic, but I will now start today.